So we're now jumping into vector calculus. And so this is basically going to tie everything we've done together in a little bow. We're going to combine all of the concepts from this semester into this more applicable subject within calculus. So before we get into some of the more key components, we're going to talk about line integrals, we're going to talk about curl, we're going to talk about divergence, surface integrals, and other ways to go about and evaluate these things. We're going to start with talking about the concept of a vector field. So I'm going to give you the definitions first, and then we'll do some examples, but I'll kind of give you another real life example of this. So a vector field on a set R in R2 is a function of the form f with an input of a point xy, where in return you get a vector. So the x component depends on the point, and the y component also depends on that point. Okay. You can extend this to R3 as well. So in that case, you're going to have a set E. So a vector field on a set E in R3 is a function of the form where now you're going to input a triple. So you're inputting a 3D point, and in return, you're getting a 3D vector. And each of these components depends on that point you're inputting. So basically the idea behind a vector field is your domain is going to be a point, but you're always going to get vectors as the return. So that is the range. So in general, a vector field is a function whose domain is a set of points and whose range is a set of vectors. Okay. So let's do a couple examples of this with an actual vector field, see what this looks like, and then I'll show you a neat application of that. So we're going to start with two different examples that both have the same directions, just sketch the vector field. We're only going to do 2D here, just because it's hard to draw by hand, but on the computer you can definitely do 3D a lot easier. So our vector field is going to be given by negative y, x. And so the basics, just if you didn't know how to graph a function before, all you did was pick points. It's going to be the same idea here. I'm going to pick a ton of different values, and then I'm just going to go ahead and plot the vectors at that particular point. So I'm going to start just by picking xy, and then finding the vector associated to that point. So you see we're putting that vector over f because it's a vector function. It's resulting in a function at the end. This is a little bit different than what we did way back in the beginning because you were only inputting a single value. So those were giving you just points at the edge of it. So you would start at 0, 0, and then it would map to the edge of it. Here I'm getting a full vector in return that's based on the point. So the points I'm going to pick are 0, 0. We're going to start with the origin. Then I'll go ahead and pick 1, 0. And then I'm going to pick some extras. You'll see I'm going to do root 2 over 2, root 2 over 2. Then I'm going to pick 0, 1, negative 1, 0, and 0, negative 1 to start. Okay. This one you might not recognize to pick. I'm just doing it for the purpose of this example, but you'll see once we go through it. But picking a lot of just simple points to work with, either on the X and Y axes, and then picking something you can even do like 1, 1, something like that. Okay. So if I plug 0, 0 into this, my Y coordinate is 0, my X coordinate is 0, so the vector that results here is exactly 0, 0. So I'm going to draw the vector field simultaneously once I get a point done. And I'm going to go out 2 in every direction. So starting with my point at 0, 0, I want to draw the vector, which is the 0 vector on that. So really at the origin, I just have a single point. Now when I plug in 1, 0, my Y coordinate is 0 and my X is 1. So this results in the vector 0, 1. Okay. So I'm going to graph this one next. So what I do is I'm going to start by plotting that point 1, 0, which is on the x-axis. And now the vector that's associated with that does not move in the x direction, but moves a length of 1 in the y. So it goes up straight for a length of 1. So this is the vector associated to the point 1, 0. Okay. Next up, we've got the root 2 over 2, root 2 over 2. Really what this does is it switches the points and negates the first component. So negative y is negative root 2 over 2, and then x is root 2 over 2. So if you think about where that point is, root 2 over 2, root 2 over 2, I picked specifically because it lies on the unit circle, because this is going to be a nice vector field. And that's right around here if you were considering, I'll even go ahead and graph that in. Here is our unit circle, and I'll dot that. Oh, let's see if we can make it actually be a circle. There we go, close enough. Okay, we'll make this gray, a lighter gray, there we go, and dotted. So there's our unit circle. That point's a little bit off, not a problem. We'll switch it back up. It's right here at that 45-degree angle. So at that point, I need to plot my vector. Now here I have a negative x component and a positive y. So I have to go negative x and positive y, and they're the same distance. So this vector roughly points off like this. So this is f of root 2 over 2, root 2 over 2. Moving on to my next point, 0, 1. Again, this just flips the point and negates the first component. So we'll graph this one next. So 0, 1 is right up here. I have negative 1 in the x direction, nothing in the y. So I go length 1 here. Okay. And then I keep doing this. My next point, again, we flip the point. So this will be 0, negative 1, negate the first, but first is nothing. So we plot this point next. So negative 1, 0 is right here. I do not move in the x direction. I have negative 1 in the y, so we go down length 1. And last but not least, we flip the point and then we negate the first component. So this really becomes positive 1. And that's down at that 270-degree angle, or the negative y-axis. And I move positive 1 in the x direction. nothing in the y. Okay. So you could pick a ton more points here. What you would see is if I pick this point on the unit circle, it would end up pointing down like this. This point here would be over like this, and this one would be over like this. Okay. So the idea behind a vector field is you can really kind of think of it like currents in the water. That's the best physical example that we have. So if I were to look at a river and I have a bunch of different vectors that are pointing the way the water is heading. So essentially, if I were to drop a feather right here, these vectors tell me how the feather would act. And so in this case, all of these are just going to keep pushing me along this circle. And so I would just keep circling back and forth and back and forth and back and forth. Okay. And I would just keep coming back to the same place over and over. So you can think of it like a little eddy or like a whirlpool, basically. But what this is called a rotational vector field. Because no matter where you pick, all you're going to do is just keep rotating around that circle. And you could see if you picked points out here, all it would do is really extend the vectors. They would have length 2 instead of length 1. And so if you dropped a feather right here, it would just rotate along a bigger circle. Okay? So let's try a second example of this. Next one we're going to look at is f of xy equaling 1/2 xy. This one's relatively nice to plot because you're not changing the point at all, you're just cutting them in half. So I'm even going to cheat because I'm going to pick exactly the same points. And I don't feel like recreating this circle, or this chart, no circle. Okay. But all I'm going to do is go ahead and get rid of these points in here because they're all going to be different. And then I'm going to go ahead and prep my graph. And I'm going to go out a distance of 2 again. Let's let it go straight. Here we go. This one down a little bit. It's a little bit too high. And again, like the last one, I'm going to go ahead and guess scotch in this unit circle because again, I'm picking points that are all along that. So we'll make it a lighter gray and dotted as well. So let's go ahead and plug each of these points in. All you're going to do is cut them in half. But when you plug in 0, 0, that does absolutely nothing. So again, at the origin, I'm going to just have a single point. So what that essentially means is if I were to drop a feather at the origin, it's not going to move at all. It's stuck there. It has no force to move it in any direction. Because these are essentially, again, you can think of them as water currents, but they're also like force fields. So it gives you the idea of where everything's heading. Or also you can think of them as wind fields, the way the wind is pointing in those directions. Next up on our vectors though, we're going to just cut each of these in half. So this next point is right here. In my x direction I move a half, in my y direction I move nothing. So I go just halfway in between. Then next up on the list here, do this one in yellow. Cutting each of those in half just gives you 4 as the denominator. Oh, that's not a 4, that's a wrong number. Here we go. Okay, so at this point, my x is positive and my y is positive, so that means I move to the right and up. And then that vector will look roughly like this. So go the same direction or same amount in each direction. Next vector up will be at the point 0, 1. So again, cutting it in half just gives you 0, 1/2. So I move 1/2 in the y direction, so I just go up halfway in between. Next one, my x component will become -1/2, and my y component is still 0. So I move -1/2, which points to the left, and that is length 1/2. Last but not least, if I pick this point, that will give me 0, -1/2 when I plug it in. So I go down 1/2. Okay. So you could pick more points on this circle, and you would see all of them really end up having the same length. Okay. So what happens here, if I drop a feather, it's immediately shooting off. If I drop a feather here, it's shooting off in this direction. Drop a feather here, it's going to shoot off in this direction. Because if I pick this point, all you're going to get is a longer vector. So it's kind of like the feather here starts and then just keeps getting shot. So it's moving faster and faster the further it gets away from the center. So this type of vector field is called a radial vector field. You'll also hear terminology later on in the semester or later on in this unit, but basically what happens is there's some source here that is pushing everything out. Okay. So one really kind of relevant application, these are actually from the most recent 2 hurricanes, is with water, but also with wind. So this is an app called Windy that kind of just gives you how the wind is moving. And so you can kind of see this was the time when there were 3 different hurricanes going on. So we had Milton in the Gulf Coast, and then I forget the other 2 names that were just out in the Atlantic Ocean. But what you can do, basically, you can see all of these different vectors that are moving and that are giving you the intensity of that wind. And then the closer you get to the eye, you can see those different like magnitude of the wind forces there. As you go around, then there's not as much wind going on in other directions, so you can see all the vectors there are really small. But in the case around the hurricane, you have those big, powerful gusts of wind. And then this one was from when Helene hit over in the Panhandle. So again, you can see this was right when it was getting in there. So in that center of the eye, these vectors are very long because they had a lot of force to them. So hopefully this makes sense why these vector fields are important for us. Again, we're going to do a ton of applications with this, but this is where we kind of get very into the physics aspect of it. So if you're taking Physics 1 or Physics 2, you should see a lot of connections between these topics. But this is kind of our start for it. So there's one last thing that we have to cover within this section, and that is a gradient vector field. So we talked about the gradient function, which again is a vector, and all of those components are just the partial derivatives. Well, since we are working with vector fields, the gradient vector is just a vector field. Okay? So a gradient vector field is a vector field of the form where you're starting with some function little f and you're taking the gradient of it. So in the case of 2 dimensions, the first component will be the partial with respect to x, and the second component will be the partial with respect to y at that point. And this is specifically in R2, or if you have a function which has triple inputs, then this vector field has three components. First is the partial with respect to x at that point, partial with respect to y at that point, and then the partial with respect to z. So if we have a vector field that's like this, where all of the components represent partial derivatives of some function, we can actually say these are conservative vector fields. Because what's going to happen is we're going to talk about the work you would need to do to kind of walk in one of these force fields. And basically in a conservative vector field, the path you take is not going to matter. So only the starting and end point will. So if you think back to physics, maybe you remember conservation of energy, but there's still kind of a connection between these. So we say a vector field F is said to be conservative if and only if there exists what's called a potential function. Which is little f, such that when you take the gradient of f, it's exactly the vector field. Okay? So we'll talk about how if you're given a vector field, can you determine if it's conservative? But all we're going to start with this time is given the function, find the gradient vector field. We'll get into the more complicated stuff soon. So for this example, we're going to find the gradient vector field of the function f of xy, which is the square root of x squared plus y squared, and we're going to sketch it. Okay. So I'm going to start just by rewriting this function. If I've got to take partial derivatives, that's x squared plus y squared to the 1/2. So if I take the partial with respect to x, I have to bring that power down. I've got to decrease the power by 1. And then chain rule, I've got to take the derivative of the inside with respect to x. Well, that only matters on that x squared piece, so you get a 2x attached. Well, the 1/2 and 2 just cancel each other out. And then we can move that 1/2 in the bottom, which is really a square root. So we get x over the square root of x squared plus y squared. And then realistically, if I take the partial with respect to y, well, all that's going to do is change what's out here. It's a 2y. So the partial with respect to y is y over the square root of x squared plus y squared. So the gradient vector field is the following. So the vector field is capital F, which is the gradient vector of this function. And so that's given by x over the square root of x squared plus y squared, and then y over the square root of x squared plus y squared. Okay. So because of this, because I took the partial derivatives or found the gradient vector of this function, we can say f is a conservative vector field. and the potential function is the function we started with. So again, in the future, what we're going to be doing is we're going to be given the vector field, have to check if it's conservative, and then figure out what function did we start with. And to give you kind of insight, well, essentially what you're going to do, if this is the partial with respect to x, you're going to integrate this with respect to x. And then you're going to have to still utilize this because some extra things can happen here. Right? But we have our vector field. All that's left to do then is we need to sketch it. So we'll pick some x, y values and figure out what is the vector associated to it. So I'll start with same kind of points. In this case, I can't use 0, 0 because that would cause me to divide by 0. But I'm again going to pick points that lie along my unit circles. So we'll do 1, 0. We'll do 0, 1. We'll do negative 1, 0. And then 0, negative 1. And then I'll pick some more from this too. But this is a good starting base. And this one, since I am going to do those more points, I'm going to go out a distance of 3 in every direction. Because we're going to find stuff on that circle of radius 2 as well. And then I'm going to go ahead and go sketch in my 2 circles. Here's the unit circle that I'm working with. If it wants to turn into a circle, there we go, close enough. And then we've got our circle of radius 2 we're going to work on after this. Okay. So all of these points I'm going to go ahead and plot in pink. We'll make that dotted. And then these points, let's go ahead and plot them in green. So starting with this first point, when I plug in 1, 0 for x, I get 1, 1, 0. So that ends up giving us 1 in the first component. And when I plug 0 in here, it'd be 0 over 1. So you get 0. So at this point, I just move 1 in the x direction. Next point is basically analogous, but now I plug in 0 for x and 1 for y. So this first coordinate is 0, and the second one will be positive 1. So we move here. When it comes to negative 1, all that does is it makes this negative, but this will still be positive when you square it and then take a square root. So this will be negative 1, and then again, nothing in the y direction. So you get this vector here. And then likewise, hopefully you see a pattern, but this becomes 0, and then that will be negative 1. So at this point, you would move down like this. And then if you picked more points along this unit circle, you would see all of the vectors here would end up having length 1. Okay. Then let's do the same thing, but on the circle of radius 2. So we'll pick the points 2, 0. Then we'll pick the points 0, 2, negative 2, 0, and 0, negative 2. I'll just go through that first one because the rest again follow in the same manner. Here you'd plug in 2, and then you'd plug in 2 for this, so you'd get root 4 in the bottom. You get 2 over 2. You end up with a 1. And then you end up with nothing in the y direction. So you'd get really the exact same vector here. And then the same thing is going to happen for all of these points. You really get the same exact vector at that next one. This one will be negative 1, 0. and then this will be 0, -1. And then if you picked more points, you would see it would just shoot out, and that vector would have a length of 1. So this is also that radial vector field. Okay? So again, you'll get lots of practice with these, but soon what we're basically going to do is we're going to see if I walk along some path inside this vector field, what would the work I do walking along that path be? Because in some points I have the wind pushing me in the right direction, in other points I'm going against it. So we need to figure out overall how much work would we do.